Counting numbers. All right, so let's try to review and remember how to count numbers, right? This may seem a little funny, but it's true. It couldn't hurt to review counting numbers, right? So, number one, counting numbers. And if you count along with me, that would be great, and it will help you quite a bit more. So, number one, counting numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, etc. You can continue counting forever, right? Up into infinity. If you can get to infinity, good luck. Okay, so how about if we go for number two, counting even numbers. So counting even numbers. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, etc., right? Okay. How about number three, counting odd numbers? Okay, counting odd numbers. 1, 3, 5, 7, 9, 11, 13, 15, 17, etc., right? So once again, you can count forever. Okay, number four, counting by three. Great. Counting by three, let's see. 3, 6, 9, 12, 15, etc., right? Takes a little more effort to count by threes, right? But it's still doable. And counting by fives, that's probably easier than counting by threes, right? For some reason. So, counting by five, starting from 25 though. 25, 30, 35, 40, 45, 50, 55, etc. All right, so there it is, counting numbers. Well, let's go to our next topic real quick. By the way, this is about sequences. Agreed? So stay tuned real quick. Here we go. Arithmetic sequences is our first topic for this particular video. So I should say that is the overall topic of this video. Arithmetic sequence. Any order list of numbers is called a sequence. Each number is a term of the sequence. So infinite sequences are continuous counting numbers. So counting numbers is a good example. Infinite sequences. Previously we were counting, right? There you are. So all of these sequences are technically infinite. You can count forever if you choose to. We also have finite sequences. Finite sequences have a finite term. For instance, if you think about gas price increments during a season or during the year. As you may notice, let's say at the beginning of the year, it starts at a lower price by comparison to, let's say, during the summertime, it's a little higher price, right? And then as it comes back to the winter again, it basically, price of gas goes down a little, at least a little, right? So let's say that would be a sequence, how it increases or how it decreases, or both combined depending on the case. But then you can probably separate into two. So infinite sequences and finite sequences. Arithmetic sequences. How can we tell if we have an arithmetic sequence? Well, the best way to tell if we have an arithmetic sequence is if the difference between any term of the sequence and the preceding term is a constant d for every such pair of terms. Then the sequence is an arithmetic sequence. We call the constant d the common difference. So common difference, just as it sounds, it's a difference, or in other words, a subtraction. Okay, so common difference. Let's go back up here with the idea of having a common difference, basically to find out if it's arithmetic or not. Okay, so common difference. Looking at our first set or order list. Okay, so our sequence. Let's start with the 1. If we're looking at the 1 and finding the common difference, we use the 2. So let's take 2 minus the 1. So 2 minus 1 will give us the common difference of 1. How can we tell it's a common difference? Well, we're going to have to check a few more terms at least. Let's go to the next one. Let's take a look at the number 2 there. So if you take the next number, so notice you're using the 2 though, looking at the 2, you're going to use the next number, which is the 3. 3 minus the 2 will give you the common difference, of this case, 1 once again. So it looks like it does have a common difference of 1. Since you're counting by ones, it's increasing by 1, right? So you're going to have a common difference of 1. Let's try the next one just for reference to make sure. 4, remember, keep in mind, you're looking at the 3, but you're using the 4. 4 minus the 3, therefore gives us 1. Okay, perfect. And let's realize that we can continue doing this forever if we choose to, for the rest of our term or for the rest of our list values. But let's check at least one more example towards the end. There we go. Let's say towards what I have at least for now. Looking at the 11, if I use the 12, there it is, 12 minus the 11, that's how we get the common difference once again, and there it is. So we call it the common difference D. So finally, there it is. It's listed for us as the common difference D, which equals 1 in this case. So for example number 1, common difference of 1. Example number 2, looking at the 2 there. Okay, so looking at the 2, we're going to take the 4 first. So 4 minus the 2, agreed? 4 minus the 2. And that gives us, in this case, 2. Let's try for the next one. Looking at the 4, we're going to use the 6 though. 6 minus the 4. So there we go. And in this case, it gives us 2. All right, let's go for the next one then. 6. Okay, looking at the 6, we're going to use the 8. 8 minus the 6 gives us, once again, 2. So we realize that we do have a common difference as well. Agreed? Now let's look at the 10 instead. I'm just going to jump one particular example for this case, but in this case, it'll make it easier. Okay, so you can keep doing it for several cases if you need it, but I recommend you do at least from the beginning one, and somewhere in the middle one, and somewhere towards the end another one. That way you can see that it's definitely a common difference between all values. So once again, doing our common difference, looking at the 10, we're going to use the 12, so 12 minus 10. And that gives us a common difference once again of 2, and that is our common difference for this particular series. Okay, going for number 3, example number 3, the 1, looking at the 1, we're going to use the 3. 3 minus 1, because it's what we're using right now, will give us 2 again. And once again, let's try an example from the end. In this case, since once again we were counting odd numbers, so we expect it to go by 2's again. So let's just double check and make sure it does work by using the last 2 examples there, or the last 2 values there, I should say. Using the 9, we're going to use the 11 first, minus the 9, right? And that gives us a common difference of 2, which is also what we noticed at the beginning. So the common difference is 2. You're welcome to check other values if needed. Okay, going for example number 4. We have the 3, using the 3, but we're also going to use the 6, the next number. So 6 minus 3. And that'll produce positive 3. And once again, going for another example. I'll go for the last example once again. Okay, in this case, we have our 18 minus 15. And it'll get a common difference once again for us of 3. So there it is, common difference in this case, 3. Going for the last example, for number 5, notice we have 25, and once again we're going to use 25 and 30, right? So 30 minus 25, and we get a common difference of 5, going for the 50 and 45, right? But you can always double check the last few problems, or the last few examples there for number 5. But in this case we were counting by 5, so it's very obvious that the common difference is going to be 5. Arithmetic sequence formula. So going for our formula real quick for reference. So a sub n equals a sub 1 plus, in parentheses, n minus 1 times the common difference d. So let me just put the values, or what it represents. A sub n is the nth value, so the actual value of the term that you want to find out, or that you currently have, depending on the case. So the nth value is the a sub n. A sub 1 represents the initial value. So what was the initial value of your sequence? And n is the nth term. What is the term number, in other words, that you're currently looking at or looking for? And of course, d, once again, we already said it, it's the common difference. So let me rewrite our formula here on the link area to make it easier to visualize. We have a sub n equals a sub 1 plus, in parentheses, n minus 1, close our parentheses, times the common difference. And if we notice, a sub n, once again, I'm just going to fill in the blanks for this one, since all we're missing is the first term and the common difference. A sub 1, your first term, is the 25. If you notice up on number 5, example number 5, it's 25 is your first term, first value term, I should say. So we plug in 25. Common difference, we figured it to be 5. So our common difference is 5. There it is. Technically, this is our formula if we want to leave it in a sequence formula format, okay? This would technically be our formula. Distributing to simplify, we are going to distribute the 5, and this is only to simplify, but otherwise you could keep it as an arithmetic sequence formula format. So we're going to distribute the 5 to the n and to the 1, okay? So do be aware of that. But otherwise we can keep it as a final value or final equation. But let's try to simplify a little bit to make it easier to visualize. Okay, so a sub n equals the 25, our initial term value, and as we distribute the 5, we get 5n minus 5. And in this case, 25 minus 5 will give us 20. So a sub n equals 20 plus 5n. And just reorganizing so that it's in decreasing exponential order. In this case, the 5n comes first, then the 20. Notice my signs did not change. So technically, this is a more simplified equation, and it will make my life easier if I need to do anything else with it. So I would normally want to simplify, but you can use it in the arithmetic sequence format as well. So I'll call this my final formula, but technically either of those two could be used as your final formula.